All right, what we're going to do next is we're going to apply this to a couple different systems. We're going to start with the simplest case first, and then we're going to move more complex, 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 until we eventually reach atoms and molecules. The very first system that almost everybody is introduced to when you start talking about quantum mechanics is the one-dimensional particle in a box. Which I always thought was really weird because can you have a one-dimensional box? No. So it's basically a particle on a line rather than a box, but we all call it particle in a box for some reason. Okay, it's a specific system that's designed to be very simple, but it illustrates many useful ideas. You've probably been wondering, how do we get the wave function? Like, how do we figure those things out? We're going to show a step-by-step procedure on how to determine a wave function starting from the Schrodinger equation in bounds. What's a system confined to? So for this system, we're going to describe it in words, and then we're going to draw a picture. We're going to consider a system a particle that is confined to a box of length A. Some people like to pick L. I like A. With a mass of M. The walls of the box are impenetrable. That might seem really silly because you were thinking, well, if I have a wall, nothing can go through it. That is not true for quantum systems. Which seems really weird. That's like if I kept running into the wall or that door, eventually I would just phase through the door. That is something that quantum particles can do. Given an infinite time scale, we might be able to do that, but the likelihood of it happening is near zero. It's not the case for quantum systems, so that's why we got to say this. The potential energy, the potential is zero inside the box, but infinite at the edges of the box. So to plot this, what variable do we want to describe a 1D system? Position? What symbol? X, thank you. All right, I was worried we were going to say Y or something. We're good. And what does this run to? What's the maximum value given what we have set up our system to have? A, yep. And what's the minimum value? Sure. You could really set any value you wanted to. 0 is the best because it makes life easier. Okay, what is the potential inside of the box again? Yep. What about when X is less than 0? What about when it's more than 0? Or more than A, I'm sorry. Okay. We're going to call these different areas, sorry, I'm trying to look for my yellow one, but I can't find it. There it is. We have 3 regions here. Region 1, region 2, region 3. Of these regions, where's the region we care about? Yeah, 2. We care about 2 because that's where the particle is going to be. However, these regions are also important when we start considering what does that wave function look like. So we set up our system, or at least we're looking at a system. The next thing we have to do are determine the bounds, those regions, and what's going on in those regions. So bounds. We have 3 regions. What are those regions again? Yeah. Okay. How would you define region 1? What's the value of x? Yep, less than 0. And what else? V is infinite. But also x can be equal to 0. Region 2, what are the values of x? Yep, and what else do I need to indicate on here? Yep, they could be equal. V is 0. And region 3. Yes, and what's the potential? Yeah. Okay. We have our regions. We've described what's going on there. Oh no, my chart. How terrible. And I hate the little broken pieces. We have our bounds. What we're going to do next is we're going to apply the Schrodinger equation in each of these bounds. We'll talk about the consequences of that and what can happen and what can't happen. Starting next class, okay? The important thing is you always want to look at what system you have, think about how does it appear, what potentials and what regions are being applied, and look at the bounds. What regions do you have? After we apply the Schrodinger equation, what we'll find is particle can't exist here, particle can't exist here. If the particle doesn't exist at those spots, what's the wave function equal to? So if it doesn't exist in those spots, what does that wave function have to be equal to? 0. We're going to find it 0 here and here, but something else here. Now let's get weird. What about on the edges of the box? Right at those points. And that's what I want you to think about next time. And possibly what functions would be 0 at these points. Okay. Are there any questions? Okay. Next time, we're going to start talking more about that. We'll figure that stuff out. If you can do this one, you should be able to do any other one that we're going to see for the next month. okay? So really think about what's going on here. After we go through the full derivation, you should be able to try and do this yourself without any notes, okay? Any questions?